Hello everyone, welcome to my channel Chemistry by ANR. The topic is specific rotation. Not only that, we will cover up enantiomeric excess as well. For knowing specific rotation or optical activity, we need to know what is enantiomer. So, enantiomers are chiral compounds. They have chiral center and they form non-superimposable mirror images. They form non-superimposable mirror images of itself. So one compound I have shown you, this is lactic acid. So the structure you can see that carbon is having four different valencies. Obviously it is the chiral center. It has one chiral center and the mirror image is being drawn. Now, using CIP rule, that is Ingold Prelog's rule, we are arranging the groups around the chiral carbon center and we are naming them R and S. So, in the first one, left hand side, we can see it is S configuration because the rotation is anti-clockwise, and in the right hand side it is R configuration. The rotation of the priority, the sequence of the priority is clockwise. So this is the configuration. The left hand side molecule is S lactic acid, the right hand side molecule is R lactic acid. Now this S lactic acid and R lactic acid, they have different optical properties. They are the stereoisomers, but they have different optical behavior. They have different optical properties. If one is dextro, the other will be levo. So for dextro I can give plus, for levo I can give minus. But they have same physical properties. Those physical properties can be boiling point, melting point, solubility, density, etc. Now the S isomer over here, the lactic acid S isomer rotates the plane polarized light towards right, and so the sign that is denoted to it is plus sign or small d, that stands for dextrorotatory. And the R isomer of lactic acid is being seen to rotate the plane polarized light towards left, and so it is the levo form as minus sign or small l. Now, this doesn't mean that the S isomer will only be dextro and R isomer will only be levo. It is not like that. It can be anything. S form can be plus or minus. R form can also be plus or minus. It just depends on the molecule. So it varies from molecule to molecule. Now, this optical behavior is being shown over here. We can see on the left hand side, I have drawn a light bulb. A light bulb is there, and on incandescence, when you light up, it emits light in all direction. That is the normal light. You can see light is being emitted in all direction. If you pass it through a polarizer and it acts, what it happens, most of the light is seen to get absorbed. Okay, it allows only certain light, certain type of light to pass through this polarizer. It allows only certain type of light in the direction of the polarizer to pass through. So that is what is shown, in the direction of the polarizer is passing through. So only the vertical portion of light will pass through here. Vertical portion will pass through, giving rise to the plane polarized light. That is polarized by the polarizer. So it is known as plane polarized light. Now when this plane polarized light is passed through the sample tube containing, say, a chiral molecule, not chiral, a chiral, then it emerges as it is. It is not rotating the plane polarized light. But if we take a chiral molecule in the say sample tube, then what will happen? Inside the sample tube you can see light of all directions, all planes. So plane polarized light, finally when it emerges, it gets rotated, it orients towards a particular direction, and there is some degree degree of rotation. Now, since there is a rotation, this is known as optical activity. That is, some degree of rotation of the plane polarized light is being observed. Now, this is one question. What I have given few compounds, say 6 compounds are drawn. Which of these molecules are optically active? Now, your work is to search for the chiral center and see if there is chiral center, if there are two chiral center. Now, in that type of molecule, if there is a plane of symmetry, POS, then that is meso and it will be optically inactive. So, we need to see them one by one. But then also, you see in the first example, first one, you have a chiral center, right? You have a chiral center and this carbon is the chiral which I have marked with the pink color. It has 4 different valencies and so it is optically active. What about compound 2? In the compound 2, you are seeing it has 2 chiral center. Fine, these are the 2 chiral centers. But there is a plane of symmetry. Because around this plane, on both the sides of this plane, the molecule is identical. So, this one is a meso compound. And the molecule itself is a chiral and it will not rotate the plane polarized light. It will be optically inactive. Now see the third one. There is no chiral center and so the molecule itself is a chiral. See the fourth one. What is happening in the fourth one? Fourth one again, this carbon is actually not chiral. Why? Because these two groups are same. This one and this one. They are identical. They are the same. So there is no chiral carbon atom. There is no chiral carbon. So it is optically inactive. Fifth one. Fifth one, you have two chiral center. This is one and this is the other. But there is a plane of symmetry. And for this reason, this compound is meso and it will be optically inactive. See the sixth one. What happens? In the sixth one, you have again two chiral center, but this one is actually not the plane of symmetry. Why? Because on one side the bond is a wedge bond, on the other side it is a dash bond. So the wedge bond is towards the viewer, the dash bond is away from the viewer. They are not symmetrical, so this is not the plane of symmetry. So since it is not the plane of symmetry, the molecule is chiral and it's optically active. So optically active, you got 1, you got 6, that these two are optically active. Now next topic which I will cover up is specific rotation, that is after enantiomer. That was my main topic. Specific rotation is denoted by alpha and its subscript is given as a wavelength. This is the wavelength lambda. Superscript is the temperature in degrees Celsius. So subscript is in terms of nanometer, wavelength in nanometer, and the superscript is temperature in degrees Celsius. And the specific rotation can be calculated as alpha observed. How many degrees is observed, the rotation, divided by L into C. L is the path length. That is the length of the polarizer into the concentration where you are giving it in terms of mass by volume, gram per ml, or at times gram per 100 ml. Now you need this unit conversions to solve numericals where 1 decimeter is equal to 10 centimeter, 1 centimeter is equal to 10 millimeter. Now next we can see that at times the subscript is denoted by capital D also. That is the sodium D line with a wavelength of 589 nanometer. Next, the topic is enantiomeric excess. Simple, it occurs when both R and S isomers are in the solution, but in unequal amount. one exists in a concentration that is more than the other. So what is the difference in the percentage? That is the enantiomeric excess. Now we have formulas to show it. Enantiomeric excess is equal to alpha observed, that is observed rotation of the solution, divided by specific rotation of one of the isomer into 100. Or this is one numerical which I have given, that if a sample has what 80% R and 20% S, then this one enantiomeric excess, if you are told to calculate, you don't need to do too many calculations, just subtract them and just check what is the difference in the two percentages, and that will be equal to the enantiomeric excess. So this is equal to mod of percent R minus percent S. That means higher minus lower. If R is higher, then R minus S. If S is higher, then S minus R. So mod is given. Next, enantiomeric excess is equivalent to the optical purity but in decimal form. That is, if I say 60%, then optical purity will be 0.60. That is what it means, that if you express it in decimal form, that is the optical purity. Enantiomeric excess is also given by this formula, that difference in the two, R minus S, divided by total of the two into 100. Now this is one numerical. See, if 16 gram of R and 4 gram of S are there, you need to find the enantiomeric excess and or express it in terms of optical purity. So you follow this. It is given by mass. So 16 minus 4 by 16 plus 4 into 100, and express it in decimal 0.60. Now 0.5 gram of a chiral stereoisomer was dissolved in 20 ml of solution. So volume of the solution is 20 ml. And what is the mass of that stereoisomer? 0.5. The observed rotation measured is minus 3 degree. So numerator is minus 3 degree. Temperature is given at 25 degrees Celsius using a wavelength 589 nanometer. Sample tube of the polarimeter is 20 centimeter long. So this is L. What is the specific rotation of the stereoisomer? Place it in the formula directly. Alpha is already given. L is given in centimeter converted to decimeter. So 1 decimeter is equal to 10 centimeter. So over 20 centimeter will be equal to 2 decimeter. Now concentration will be mass by volume. So mass is given 0.5 gram. Volume is of the solution is 20 ml. So it will be 0.025 gram per ml. That is 0.5 by 20. Now when you place the values, you will get the specific rotation. This is the specific rotation, minus 60 degree. Now here I have given just the summary. What is the enantiomeric excess? It is a way to express how much one enantiomer is present in excess over the other in a mixture of the two enantiomer. Now it is the difference in percentage of the two enantiomer in a very simple manner, you can say. So if I say the enantiomeric excess is 0%, that means no difference is there. It is in equal amount, 50:50. So it forms a racemic mixture, and such mixture with having enantiomeric excess value 0% will be optically inactive. If it is 100%, means it is the pure enantiomer. If S is there, then S. If R is there, then R. If higher value is there, that means higher optical purity is there. Now again, what is the summary of that optical purity? It is the percentage of one enantiomer which is in excess over the racemic mixture. So it is numerically equal to the enantiomeric excess, only you express it in the decimal form. So optical purity is equal to observed rotation by rotation of the pure enantiomer into 100. If the pure compound shows a rotation of 50 degree, what does it mean? Then the observed rotation, suppose, is equal to 20 degree. Then these two means that optical purity will be observed by the pure compound, rotation of the pure compound. So 20 by 50 into 100 expressed in percentage. Now, if it is a 0% optical purity, that means it is again a racemic mixture and it will be optically inactive. And 100% optical purity means it has a pure enantiomer. So I hope the concept is clear. Do revise, give pauses to the video and understand better. Please follow the post section of the channel where I give a quiz or a poll for you to answer. Bye all of you.